Hello, my darlings. Okay, so today we're going to look at Newton's law of cooling. So this law states that the rate at which the temperature T of a cooling body is proportional. So remember, the rate at which the temperature is changing is proportional to the difference between the temperature of the body and the constant room temperature, the environmental temperature. Now be careful, this T naught is now not the temperature at time zero, it's the environmental temperature. It's the temperature of the area around whatever it is that's cooling, okay? So be careful with that. And that can actually get substituted in before you solve the differential equation. That's not a variable usually, okay? Now, I know having capital T's and lowercase t's can be confusing to you, so sometimes people will change this to dy dt equals k times y minus, again, that's going to be the temperature of the environment. Okay, so let's look at a problem. Suppose that at 1 p.m. one winter afternoon, there is a power failure at your house in Wisconsin, and your heat does not work without electricity. When the power goes out, it is 68 degrees Fahrenheit in your house, and at 10 p.m., it is 57 degrees Fahrenheit in the house, and you notice that it's 10 degrees Fahrenheit outside. So let's see what we know. So this starts at 1 p.m., okay, when the power goes out. So 1 p.m. is going to be our time zero. And we know that our temperature in the house is 68 degrees. Okay. Then later on at 10 p.m., so if 1 o'clock is 0, 10 o'clock is T equals 9. And we know that the temperature in the house is 57 degrees. And we also know that it's 10 degrees Fahrenheit outside. That's the temperature of the environment. That's T naught is 10 degrees Fahrenheit. Now remember, for Newton's law of cooling, we have dt over d little t equals the constant of proportionality times T minus T naught. So all we've done so far is read the stem of the question and write down what they told us, okay? Now let's see what they're asking. Assuming that the temperature T in your home obeys Newton's law of cooling, write a differential equation satisfied by T. So that's why we used this differential equation here. So we're going to do dt over d little t equals k times T minus, and the only thing we can substitute in is the 10 for the temperature in the environment. That's it. That's part A. We wrote our differential equation. Now, we're going to solve the differential equation. So the first step is solve the differential equation to estimate the temperature of the house when you get up at 7 a.m. So now hold on, 7 a.m. Now remember, 1 p.m. is 0, so 7 a.m. is time 18, and we want to know the temperature in the house at that time, okay? So we start with our differential equation, dt equals k times capital T minus 10. Now we need to separate the variables. Capital T is to the left, lowercase t is to the right. So that means we're going to divide, and we have dt over t minus 10 equals k times dt. Now we're going to integrate both sides. Now because the derivative of t minus 10 is 1, I can do 1 over t minus 10 and integrate that to the natural log of the absolute value of t minus 10 without doing a u substitution. That works because the derivative of t minus 10 is positive 1. Equals the antiderivative of k dt is kt plus our constant, okay? Now we have a natural log equation. To solve a log equation, we change it to exponential, so it's the absolute value of t minus 10 equals e to the kt plus c1. Now we want to get rid of our absolute values, which means we have to make sure the other side could be positive or negative. And when we have addition in an exponent, that means we had e to the kt times e to the c1. But we know that plus or minus e to the c1 is just another constant, which we'll call c2, and we have times e to the kt. Okay, so we've substituted in, and I'm going to close this off a little bit so we can see what we're doing. Now, the next thing we're going to do is we're going to use one of those initial points that they gave us. They told us that at time 0, the temperature is 68 degrees. So we're going to do T of 0 equals 68, and we're going to substitute in, okay? So when we plug in here, we will have 68 for the temperature minus 10 equals C2 e to the 0 times k is 0. Now 68 minus 10 is 58 equals C2 times e to the 0 is 1, so it's just C2 is 58. Now we know, and we're going to substitute that back in here, we know that T minus 10 equals not C2, but 58 e to the kt. Now we're going to use the next point that they told us, which was that at time 9, the temperature is 57 degrees. So at time 9, our temperature is 57 degrees, and we're going to substitute that into this equation. 57 minus 10 equals 58 e to the 9k. All right, so that's going to give us 47 equals 58 e to the 9k. And then we divide, so 47 over 58 equals e to the 9k. Now we have an exponential equation to solve that. We put it in log form. So a log base e is the natural log of 47 over 58 equals the exponent 9k. And if we divide by 9, we have k is 1/9 times the natural log of 47 over 58. Whew. Okay, so that means T minus 10 equals 58 e. Now I have to multiply T times that K, so I'm going to write a T over 9 times the natural log of 47 over 58. All of that in that exponent. Okay, but we're not done. We're going to solve that for T. So in order to solve that for T, all we have to do is add the 10 to the other side. And remember, what are we supposed to be finding? The temperature when the time is 18. So we're going to do T of 18. That's going to be 10 plus 58 e to the 18 over 9, natural log of 47 over 58. So this is 10 plus 58 e to the 2, natural log of 47 over 58. Now technically, yes, this is your exact value, but it's not really useful to us, is it? So you're going to go to your calculator, and we're going to type this in the calculator. And when we do, it should come out to about 48.086 degrees Fahrenheit. So now there was another question, though. Should we worry about our pipes freezing? No, because remember, freezing is 32 degrees Fahrenheit, so no, we do not need to worry about our pipes freezing. Now, this is a question you might actually have to worry about as an adult, as a homeowner, depending on where you live. You always say, when am I going to use this stuff? Since the temperature is above freezing, which is 32 degrees Fahrenheit. And it's no fun when your pipes freeze. I have had that happen. It's not a fun thing. Okay, so now let's see. One last part. What assumption did we make in part A about the temperature outside? We assumed a constant temperature. Okay. Now, given that probably incorrect assumption, because the temperature doesn't stay the same outside all day long, from 1 p.m. through the night to 7 a.m. the next morning. It doesn't happen, right? The temperatures, was there sunshine? Are there clouds? because it might get warmer between 1 and 3. Depends on where you are, what time of year it is. Is there the darkness, right? Does the temperature drop overnight? So it might actually be colder in the house than our estimate, but it's an estimate, okay? And there we go. Newton's law of cooling and a practical application. Have a great day, guys. See you soon.